Welcome back to the Deep Dive, your express lane to genuine understanding. We cut through the noise, deliver the essential insights you need. Today, we're plunging into a technology that's really redefined how we think about data, MongoDB. We have a definitive guide right here, and our mission is simple. Distill its most crucial concepts, maybe some surprising facts, and definitely the practical applications. By the end of this deep dive, you'll not only understand what MongoDB is, but crucially, how its unique approach could fundamentally change the way you think about, well, building your own projects.
It's a really compelling journey because MongoDB truly shifts the paradigm away from traditional relational databases. It champions a different philosophy for data storage, one that's fundamentally designed for flexibility and, maybe most importantly, for horizontal scalability. That's a huge departure.
Exactly. We're here to give you that shortcut, empower you to navigate the world of modern databases with confidence. Let's get started. So, at its very foundation, MongoDB is what we call a document-oriented database. Now, if you're coming from the world of SQL, rigid rows and tables, this is a real conceptual leap. For you, the curious learner or developer listening, what does this fundamental shift actually mean in practice?
Well, the core insight here is that instead of forcing your data into predefined tables and rows, MongoDB embraces a flexible document model. Think of it like maybe a JSON object or a Python dictionary you're already used to working with.
Okay.
This allows you to represent complex hierarchical relationships, like imagine an entire blog post complete with its author details, tags, and all its comments all neatly contained within a single record. And this naturally aligns with how modern developers think about objects in their code. And crucially, it's a design choice that makes scaling out much, much easier down the line.
That concept of a document is powerful. So let's get into the specifics then. What exactly constitutes a MongoDB document?
At simplest, a document is just an ordered set of keys with associated values. Like in any language, there are a few important rules. Keys can't contain the null character, 0, and characters like the dot and the $ doll have special meaning within MongoDB, so you'll typically avoid them in key names.
Yeah.
And you have to remember, it's both type sensitive and case sensitive. So age with a capital A and age lowercase are completely different keys.
Got it.
And every single document must have an id key for unique identification. Usually, MongoDB just generates one for you and objected.
Okay, so every document gets a unique id. But, if documents are so flexible, why do we even need separate collections?
Yeah.
It feels like you could just throw everything into one big pool. What's the strategic advantage there?
That's a great question, and it's a common initial thought, actually. The core insight here is that while MongoDB offers incredible schema flexibility, establishing logical collections, separating your users from your products, from your orders, is absolutely critical for maintainability, for efficient querying, and just overall development sanity in real-world applications.
Okay, sanity's good.
Yeah, it makes administration easier. It allows for more focused and efficient indexing, especially unique indexes for specific types of data. And it provides clear boundaries for, say, defining schemas through validation when you do need to impose some structure later on. It's about using that flexibility without sacrificing necessary organization.
Makes sense. Now that we've grasped the individual document and how collections help organize them, let's zoom out a bit. What about the databases themselves? Are there rules or special considerations when creating and managing those?
Yes, databases in MongoDB also have their own naming rules. No characters like /, /, or dot, and they're limited to a maximum of 64 bytes. There are also important reserved names you'll definitely encounter. Admin, which handles user authentication and authorization.
Right.
Local, which stores server-specific data like replication info and it's never replicated itself.
Yeah.
And config, which is essential for sharded clusters, it stores metadata about the cluster. You'll also hear the term namespace. That's basically just a fully qualified collection name like cms.blog.posts, and that is limited to 120 bytes.
That sets the stage for the architecture. So, for someone just dipping their toes in, how easy is it to actually get up and running, to start playing with MongoDB?
Surprisingly easy, actually. You'll mainly interact with two components. First, there's Mongod. That's the actual server process, your database engine.
The Mongon.
And then there's Mongo, which is the command line shell. That's your primary interface for interacting with Mongod.
And when you fire up that Mongod server, what are some of the first things you need to know, like its default setup?
Well, by default, MongoDB will try to use DataDB for its data directory, or DataDB on Windows, and it listens on port 27017. Now, here's a really critical piece of advice. Always prioritize security from day one.
Always.
Make sure your MongoDB instances are properly secured before deploying anything to production. Our source material goes into depth on this later, but it's paramount. The Mongo shell itself is far more than just a simple command line. It's actually a fully functional JavaScript interpreter.
Oh, interesting.
Yeah, which makes it an incredibly powerful tool for everything from administration to complex data manipulation.
Okay, so once you understand MongoDB's core philosophy, the next natural step is getting your data in and out right.
Yeah.
How do we start building our applications? Well, it begins with basic operations like adding documents. For just a single record, you'll reach for the insert tone method. Pretty straightforward.
Yeah, and for larger operations, you'll definitely want insert many. This is much more efficient for bulk inserts because it cuts down the number of round trips to the database. There's a practical 48 millib limit per batch, roughly, and you can choose between ordered inserts, where processing stops if there's an error,
Okay.
and unordered, where MongoDB tries to insert all the documents regardless of individual errors. Unordered is often faster.
Gotcha. And when it's time to remove data,
You've got delete one and delete many. They provide clear ways to selectively prune your documents based on a filter you specify. And if you want to completely swap out a document, just change the whole thing. You use replace one.
okay, so we've covered the basics of putting data in and taking it out. But what if you only need to tweak, a tiny part of a document? Or maybe increment a counter without fetching the whole thing back and forth.
Yeah.
That's where I hear MongoDB has some really powerful, almost magical atomic operators. Tell us more about those.
You're absolutely right. These are game changers for efficiency. If you only need to modify specific parts of a document, MongoDB gives you operators that do this atomically, right on the server. You have inc for incrementing numeric values, set for setting values, or even embedding entire subdocuments like an author.name.
Nested updates.
Exactly. For arrays, there's push to add elements and pull to remove them based on some criteria. And for really granular control within arrays, the positional operator, just the $sign, is incredibly useful. It lets you update a specific element that matched your query criteria.
And these atomic operations often combine with something called upserts, right? What's that about?
Precisely. Upserts basically mean update if found, otherwise insert.
Ah, okay.
Yep.
Update or insert.
Yep. This is fantastic for avoiding race conditions and significantly reducing your application code complexity, especially for things like page view counters, where you want to increment a count or just create it if it doesn't exist yet. I've seen so many developers write complex if-then-else logic for this, when upsert just handles it beautifully in one go. There's even set and insert for fields that should only be set when a document is first created during an upsert. Just remember the distinction. Update 1 modifies just the first document it finds, matching your filter, while update many affects all documents that match.
Okay, super useful. Now, once your data is in, the next challenge is finding exactly what you need. The find method seems to be the workhorse for querying. For basic queries, you just provide key-value pairs, right?
Yeah.
And if you add multiple conditions to your query document, MongoDB treats them as an A&D operation.
That's correct. But to go beyond simple equality, you use query conditionals. Operators like dalt for less than or equal, general dalt for greater than or equal to those handle ranges. Then you have none dollars for not equal. And $1 is useful if you want to match a single key against multiple possible values, like finding users in a specific list of countries. For more complex scenarios, door allows you to query for documents matching any of the conditions you provide, maybe across different keys or involving complex logic. What's really ingenious here is that unlike other compound queries, door is unique in its ability to potentially leverage multiple indexes, one for each clause in the door array. That can make it very powerful for certain search patterns.
And if you don't need the entire document back every time, you can use projection, right, to specify just the keys you want.
Exactly. You provide a second document to find specifying the fields to include or exclude. Just remember that theta is always returned by default unless you explicitly exclude it using EH0.
Got it.
For arrays, you can use size to query for documents where an array has a specific length, but here's a common stumbling block I see.
Oh, yeah.
When you need to match multiple conditions within an embedded document inside an array, like a comment having a specific author and a certain score, that's where LMatch is crucial. It helps you group your criteria to ensure both conditions apply to the same embedded document in the array, not just finding any comment by that author and any comment with that score in the same post.
That's subtle but important. Okay, so when you run a find query, you don't just get a big list of data back immediately. You mentioned something called a cursor.
Right. The database returns a cursor. Think of this cursor as your dynamic window into the query results. It's how you navigate and interact with the data as it becomes available, rather than loading everything into memory at once.
Okay, so it's more efficient.
Much more efficient, especially for large result sets. And a key aspect of cursors is their laziness. The query isn't actually sent to the server until you start requesting results from the cursor. This is brilliant because it allows you to chain operations like sort, limit, and skip onto your find call before the query is even executed. You build the query plan incrementally.
So you can build up complex queries piece by piece.
Exactly. You iterate through the results using methods like hasNext and next, or often more conveniently, using for each. Oh, and another thing, server-side cursors have an automatic 10-minute timeout for inactivity. This is a clever way to prevent resource drain if a client application, say, crashes or just stops processing results midway.
That's smart. Now, you mentioned skip for pagination, but I've heard that can get slow on big data sets.
Yes, absolutely. Using large skip values forces the database to essentially step over all those skipped documents, which gets progressively slower.
Oh, what's the better way?
A much more efficient technique, a real pro tip, is to use range-based pagination. Instead of skipping, you use the value of a sorted field, like id or a timestamp, from the last document of the previous page as a query criterion for the next page.
Ah, like find me everything greater than this last ID.
Precisely. .find.sort. Sort it. Last aside. NIZ1. Page size. This lets the database jump directly to the starting point using an index, making pagination much faster and more responsive, especially on large collections.
Okay, that makes a lot of sense. Let's talk about optimizing these queries. Indexes seem absolutely critical for performance. How do you create them? And, more importantly, how do you know if they're working?
Right, you use the createIndex method on a collection to define them. To really understand what's happening under the hood and whether your index is effective, explain execution stats is your best friend.
Okay.
You run your query with .explain execution stats appended. The output shows you crucial metrics like n returned, how many documents actually matched, total docs examined, how many documents MongoDB had to look at to find the results, this is key, and execution time millis. Comparing total docs examined with and without an index powerfully illustrates the dramatic difference. A good index drastically reduces the documents examined, often bringing it close to n returned.
And you can create indexes on more than one field, right? Compound indexes.
Yes, compound indexes are very common. You index on multiple fields like user-id, 1, created at magnif1. The beauty here is that you often get several indexes for the price of one. Any prefix of that compound index is also implicitly indexed.
Oh, so in that example, an index on just user-id would also be covered.
Exactly. You get a free performance boost for queries that only filter or sort by user-id in this case.
That's handy. Now, this might sound counterintuitive, but you always hear indexes, indexes, indexes for performance. Are there times when an index is actually not a good idea? When might it hurt performance?
That's a really important question, actually. Indexes are amazing for retrieving small, selective subsets of data quickly. That's their sweet spot. However, they become less efficient as the query needs to retrieve a large percentage of the total documents in a collection. Why? Because using an index typically involves 2 lookups per document. One to find the entry in the index, and another to follow the pointer from the index to the actual document on disk or in memory.
Right, 2 steps.
Whereas a full collection scan just reading through all the documents sequentially only requires 1 lookup per document. So if your query is going to return, say, 30%, 50%, or more of the collection, a collection scan can actually be faster because it avoids all those extra index lookups. It's about understanding the selectivity of your query.
Okay, so MongoDB isn't just a generalist database. It sounds like it has some really specialized tools for unique needs, helping you tackle specific data challenges beyond just standard CRU operations.
Yes, definitely. One really useful specialized tool is TTL, or time to live, indexes. These are fantastic for data that should automatically expire.
Like what? Caches? Session data?
Exactly. Caches, session storage, maybe temporary logs.
Yeah.
You create an index on a date field with an expire after seconds option, and MongoDB will automatically delete documents once that time passes relative to the indexed field. It sweeps these indexes roughly once per minute to clean things up.
Cool.
We also have geospatial indexes, which are fundamental for location-based queries. They let you use operators like geointersects, geowithin, and near to find documents based on geographic coordinates. Think store locators or location-aware services.
Makes sense.
And there are full-text indexes for efficient string searching within your documents using operators like text and search.
Now, earlier when we talked about replica sets, you mentioned the oplog being a capped collection. Can you explain what a capped collection is in more detail? What's special about it?
Absolutely. Capped collections are another specialized type. These are fixed-size collections that work on a FIFO basis, first in, first out. Once they reach their configured size limit, they automatically overwrite the oldest documents to make space for new ones. This makes them potentially useful for things like high-volume logging or storing very recent activity streams.
Okay, like a circular buffer.
Pretty much, yeah. Though it's worth noting that with the modern WiredTiger storage engine, TTL indexes and another feature called change streams often provide better, more flexible alternatives for many of the use cases where capped collections were traditionally used.
Right. And what about storing really large files, like images or videos? Does MongoDB handle that?
Yes, for that, MongoDB offers GRID FS. It's a specification for storing files larger than the standard 16 MB document size limit by breaking them into smaller chunks, typically 255 KB each, and storing those chunks in separate documents along with metadata. There's a command line tool, Mongo Files, that helps you interact with GridFS. However, it does have downsides.
Such as?
Well, it's generally slower than accessing files directly from a file system, and you can't modify files in place. If you need to change even a small part, you have to replace the entire file, which can be inefficient for frequently updated large files. So you weigh those trade-offs.
Okay. Now, for more serious data analysis and reporting, beyond simple queries, you need the aggregation framework. You described it as building a powerful data processing pipeline. Unpack that for us.
That's a great analogy. The aggregation framework lets you process data records and return computed results. You use the aggregate method, passing it an array of documents. Each document in that array represents a stage in the pipeline, using a specific aggregation operator.
So data flows through these stages.
Exactly. Data flows through the stages sequentially. For example, you might start with a match stage to filter documents early on, very important for performance. Then maybe a project stage to reshape the documents, perhaps selecting only certain fields, renaming them, or even creating new computed fields.
Right.
Another common stage is unwind. If you have documents with arrays, unwind deconstructs the array, outputting a separate document for each element in the array. This is super useful for processing array contents individually.
And when you're looking to summarize or group your data, like calculating totals or averages,
Yeah.
how does that work in the pipeline?
That's where the group stage comes in, often used with accumulators. Accumulators are operators used within group to perform calculations across the documents being grouped. Examples include sum for adding values, abg for averages, max, the modders, and even push, which can collect values from the grouped documents into a new array.
Right, so group lets you categorize things.
Precisely. If we connect this to the bigger picture, the group stage, particularly how you define its id field, is incredibly powerful. You use the id to specify the key you want to group by. This could be a single field, multiple fields combined into a subdocument, or even fields within embedded documents. It allows you to categorize and summarize your data based on almost any criteria, giving you deep insights and turning raw data into meaningful reports.
Very cool. Now let's talk about a major evolution in MongoDB, multi-document ACD-compliant transactions. This was a truly monumental leap for the database, wasn't it? What does AC compliant actually mean here?
It was huge, yes. AC stands for atomicity, consistency, isolation, and durability. In simple terms, a transaction is a logical unit of processing involving one or more operations. Atomicity means the entire transaction either completely succeeds all its operations commit or it completely fails, and all its operations roll back, leaving the database unchanged. Consistency ensures the transaction brings the database from one valid state to another. Isolation means concurrent transactions don't interfere with each other, and durability guarantees that once a transaction commits, its changes are permanent, even if the system crashes.
And why is that so important?
It's absolutely critical for operations that need to update data across multiple documents or even multiple collections reliably. Think of an e-commerce order. You might need to simultaneously update an orders collection and decrement stock in an inventory collection.
Right, you need both to happen or neither.
Exactly. If one part fails, maybe the inventory update fails, you need the whole operation undone so you don't have an order recorded without the corresponding inventory change. ACID transactions guarantee that all or nothing behavior.
Okay, and MongoDB provides different ways to work with transactions.
Yes. There are two main APIs. A core API, which gives you fine-grained control similar to traditional relational databases, and a callback API. The The callback API is generally recommended because it has built-in logic to automatically retry transactions in case of certain transient errors, like temporary network issues or primary elections, which simplifies application development quite a bit.
That sounds helpful.
And it's worth appreciating the engineering effort behind this. Implementing multi-document ACID transactions was a multi-year project involving deep changes to MongoDB's internal architecture. This included things like a new replication consensus protocol, RAFT, and a global logical clock to coordinate operations across the distributed system. It really transformed MongoDB into a system capable of handling complex, mission-critical operations with strong guarantees.
Wow. Any catches or things to remember when using them?
One crucial detail. CRUD operations within transactions must be performed on existing collections. You can't, for example, create a new collection inside a transaction. The collections have to exist beforehand.
Good to know. Now, shifting gears slightly, you mentioned earlier that schema design is arguably the most important aspect for performance in MongoDB. This feels like a fundamental shift from maybe traditional database design, where the structure is more rigid up front.
It absolutely is. The core principle is designing your schema based on how your application actually accesses the data. You prioritize your most common queries.
So performance drives the design.
Largely, yes. You also consider things like separating dynamic, frequently written data from more static, mostly read data, maybe put them in different documents or even collections. And the really critical choice, the one that comes up constantly, is embedding related data versus referencing it using IDs.
Okay, explain that trade-off. Embedding versus referencing.
Right. Embedding means putting related data directly inside the main document, like putting all the comments directly inside the blog post document. This often makes reads much faster because you can get all the related data in a single trip to the server. One query, all the info.
That sounds efficient.
It is, for reads. However, referencing storing just an ID of the related document, like storing an authored in the post and keeping author details in a separate authors collection, can make writes faster, especially if that related data changes frequently. It also reduces data repetition. If an author's name changes, you only update it in one place in the author's collection, not in every post they ever wrote.
The classic normalization versus denormalization trade-off.
Exactly. You have to decide which trade-offs make sense for your application's primary use cases. Are reads more critical? Are writes? How often does the related data change?
That makes total sense for fast reads with embedding. But isn't there a risk of having extremely large documents or maybe a lot of redundant data if that embedded information changes frequently? How do you balance that?
You've hit on the precise trade-off. It's definitely not one size fits all. And yes, embedding everything can lead to large documents or update anomalies. That's why there are established schema design patterns you can leverage to mitigate these risks. The polymorphic pattern, for example, is great when you have documents in the same collection that are similar but not quite identical in structure. Maybe different types of products with some shared fields, but also unique ones.
Okay.
There's the approximation pattern, which is useful for things like high-frequency counters like page views. Instead of updating the counter on every single view, which can cause contention, you might batch updates, maybe update the counter only every 100 views. It's an approximation, but often good enough and much more efficient.
Interesting.
And the document versioning pattern helps if you need to retain old revisions of documents, maybe for compliance or history tracking, without constantly duplicating the entire main record. You store older versions separately.
Can you give us a quick, concrete example of that normalization versus denormalization trade-off?
Sure. Let's use a classic. Students and the classes they're enrolled in. A traditional relational normalized approach might have a students collection, a classes collection, and a separate enrollment or join table collection that just links student IDs to class IDs. To get a student in all their classes, you'd need multiple queries or join potentially slower reads.
Right.
A fully denormalized embedded approach might put an array of class details, like class name, teacher room number, directly inside each student document. Now, getting a student with their classes is incredibly fast one-read operation.
Right.
But if a class detail changes, say, the room number for Biology 101 changes, you'd potentially have to find and update that information inside every single student document enrolled in that class. That could be a very slow write operation.
Okay. So you choose based on read versus write frequency.
Exactly. If your application reads student data with their classes far more often than class details change, embedding might be the winner. If class details change often, referencing might be better.
And finally, there's this phenomenon, sometimes called the Will Wheaton effect. What happens when a single document, like maybe a celebrity's list of followers in an array, grows incredibly large and unwieldy, potentially even exceeding the 60 millibyte document size limit. How do you manage that?
That's a great example of a practical scaling problem with embedding large arrays. When a single document threatens to grow too large due to an unbounded array like followers or comments, you can use what's sometimes called an outlier or bucket pattern. Instead of storing all followers in one array, you might break them up. Maybe the main document stores the first 1,000 followers, and if it exceeds that, you create a separate continuation or bucket document linked to the main one to hold the next 1,000, and so on. It's a way to manage potentially infinite growth within the document size constraints.
Okay, let's talk scaling and reliability. Replica sets seem to be MongoDB's robust answer to high availability and making sure your data is redundant. How do they actually achieve this protection?
Right. Replica sets are fundamental for production deployments. The core mechanism behind them is the op log, which stands for operation log. Imagine it like a continuous, real-time ledger of every single write operation, insert, update, delete, that happens on the primary server in the replica set.
Okay, the master record of changes.
Exactly. This op log is actually stored as a special type of collection, a capped collection as we discussed, usually in a database called local on the primary server. The secondary members in the replica set constantly read from this op log on the primary and apply the exact same operations in the exact same order to their own data copies. That's how they stay in sync or replicate the data.
And you mentioned capped collection. Does the oplog size matter?
Oh, absolutely. Op log sizing is critical. If a secondary falls too far behind, maybe it was offline for maintenance, and the operations it needs are no longer in the primary's capped op log because the op log wrapped around, it might need to do a full resync, which can be resource intensive. A good rule of thumb is to size your op log large enough to hold at least 24 hours of operations, preferably more like 2-3 days, depending on your write volume and maintenance windows. This provides a safe buffer.
Okay. And how does a replica set decide which member is the primary? How does it handle failover?
That's handled through an election process. If the current primary becomes unreachable, the remaining secondaries hold an election based on a consensus algorithm, like RAFT. The crucial concept here is the majority rule. A member can only be elected primary and remain primary if it can communicate with a majority, more than half of all voting members in the set. This prevents split-brain scenarios where you might accidentally end up with two primaries writing conflicting data if the network partitions. You need a majority to operate.
That makes sense. Now, when it comes to writing data to a replica set, you mentioned write concern earlier. How does that play into reliability?
Write concern is how you tell MongoDB what level of acknowledgement you need for your write operations. You can specify W.1, just wait for the primary to acknowledge, or for higher durability, you might use W majority.
W majority. So that waits for.
It waits for the write operation to be successfully applied not just on the primary, but also replicated to a majority of the voting members in the replica set before acknowledging success back to your application. This significantly reduces the risk of data being rolled back if the primary fails shortly after the write but before it replicated widely.
Okay. Safer, but maybe slightly slower writes.
Potentially, yes. There's also a JTrue option for write concern, which ensures the write has been written to the on-disk journal on those members, providing even stronger durability guarantees. And similarly, for reads, you have read concern. Options like local, read the latest data from the member you're connected to, might be slightly stale. Majority, read data that's been committed to a majority, ensuring it won't be rolled back. Or even linearizable, the strongest guarantee, ensuring you read data that reflects all successful majority writes that completed before your read started, offer different consistency levels.
So this really raises an important question for the listener. How do you balance the need for performance versus the need for strong consistency and durability for your specific application's requirements? It sounds like MongoDB gives you the knobs to tune that.
Exactly. It gives you control, but you need to understand the implications of those settings.
Are there different types of members you can have in a replica set besides just primary and secondary?
Yes, MongoDB allows for some special member configurations. You can have arbiters. These are members that participate in elections. They vote, but they don't actually hold a copy of the data. They're lightweight tiebreakers, useful for achieving an odd number of voting members to ensure a majority can always be formed without the overhead of storing data.
Yeah.
You can also have hidden members. These hold data and replicate like secondaries, but they're invisible to client applications for read operations and can never become primary. They're often used for dedicated tasks like running backups or offline analytics without impacting the main workload.
Smart.
And finally, there are delayed members. These also hold a full data copy but are configured to lag behind the primary by a specific amount of time, say an hour. They act as a rolling backup, providing a window to recover from certain types of human error, like accidentally dropping a collection. You could potentially restore from the delayed member before the deletion replicated there.
Okay, very useful options. Now, what happens when a single replica set isn't enough? When you need to scale beyond the capacity of even the largest single server or set to handle truly massive data sets or write loads?
That's when you shard. Sharding is MongoDB's approach to horizontal scaling. It partitions your data across multiple replica sets called shards. This allows you to distribute the data, the storage load, the RAM usage, and the I/O operations across many machines, scaling almost linearly.
Okay, so you break the big database into smaller pieces distributed across multiple replica sets. What are the main components of a sharded cluster?
A sharded cluster has three main components. First, you have one or more Mongo's processes. These are lightweight query routers. Your application connects to a Mongo's, not directly to the shards. The Mongo's figures out which shards hold the data needed for a query and directs the query accordingly.
So Mongo's is like the traffic cop.
Exactly. Second, you have the config servers. These store the cluster's metadata information about which collections are sharded, what the shard key is, and the mapping of data ranges, called chunks, to the specific shards. Since MongoDB 3.2, config servers must be deployed as their own replica set for high availability, which is a huge improvement.
Okay, the brains of the operation.
Sort of, yeah. And third, you have the shards themselves. Each shard is typically, and since MongoDB 3.6 must be, a full replica set providing high availability for the subset of data it holds.
Got it. Now, the critical decision point in sharding you mentioned is a shard key. That sounds really important. What is it and why is choosing the right one so crucial?
The shard key is absolutely paramount. It's a field, or potentially multiple fields, that exists in every document within the collection you want to shard. MongoDB uses the value of the shard key to determine which chunk a document belongs to, and therefore which shard that chunk and document should live on. Choosing a good shard key is critical for ensuring even data distribution and efficient query routing. A bad shard key can lead to hotspots where most of the data or activity lands on a single shard, negating the benefits of sharding or inefficient queries that have to hit every single shard, scatter-gather queries.
Okay, so what makes a good shard key? What are the strategies?
There are a few main strategies. One is hashed sharding. Instead of using the raw key value, MongoDB computes a hash of the shard key field's value. This results in a very random, even distribution of data across the shards.
When would you use that?
Hashed sharding is great for avoiding hotspots, especially when your shard key is something that increases monotonically, like an id or a timestamp. If you use the raw timestamp, all new writes would always go to the same shard. Hashing spreads them out randomly. The other main strategy is ranged sharding. Here, MongoDB divides the range of possible shard key values into contiguous chunks. For example, if you shard on zip code, one shard might hold zip codes 000000000000009999 and another 570999999. You can also use compound shard keys combining multiple fields. This allows for more controlled distribution and can support range queries on the leading fields of the key. A common pattern is sharding by something like customer ID for good distribution, and then ordered date to keep a customer's orders together and support date range queries for that customer efficiently.
How can you tell if your queries are using the shard key effectively?
Again, explain is your friend here, even in a sharded cluster. When you run explain on a query via Mongo's, the execution plan will tell you if the query could be targeted to a single shard, indicated by single shard stage, because it included the shard key effectively, or if it had to be broadcast to multiple or all shards, shard merge or shard query stages. Seeing lots of scatter-gather queries often indicates a suboptimal shard key or query pattern.
Okay. And is there anything more advanced for controlling data placement?
Yes, for more fine-grained control, there's zone sharding, sometimes called tag-aware sharding. This allows you to define zones, groups of shards, and associate specific ranges of shard key values with those zones. For example, you could ensure that data for European customers resides only on shards physically located in your European data center, maybe for data sovereignty or latency reasons. It gives you control over data locality within the cluster.
Very powerful. So once you've deployed MongoDB, whether it's a replica set or a sharded cluster, how do you keep an eye on its health? How do you monitor it, make sure everything's running smoothly?
Monitoring is crucial. There are several key built-in tools. db.currentautopy is invaluable. It lets you see all the operations currently running on the server, how long they've been running, and what they're waiting on. Great for spotting long-running queries or identifying bottlenecks.
Okay.
Then there's the system profiler. You can enable it using db.set profiling level. Level 2 profiles everything, which can be resource intensive, so use it carefully. Level 1 profiles only slow operations, those exceeding a configurable Sloan's threshold, for example, 100 milliseconds. The profiler logs detailed information about slow queries, which is essential for diagnosing performance issues.
So you can find exactly which queries are causing problems.
Exactly. And there are also useful command line utilities that ship with MongoDB. MongoTop gives you a real-time, top-like view showing which collections are experiencing the most read-write activity. MongoStat provides a continuous stream of server-wide statistics operations per second, network traffic, queue lengths, page faults, etc., giving you a high-level overview of server health. These are your go-to diagnostics toolkit.
Memory seems absolutely critical for database performance in general. What specific memory metrics should you be watching in MongoDB?
Yes, memory management is vital. You'll typically track a few key metrics. Resident memory is the amount of physical RAM MongoDB is actively using. Virtual memory is the total address space allocated by the OS, which can be much larger. With the WiredTiger storage engine, the default now, the key concept is its internal cache. The ultimate goal is to ensure your application's working set, the data and indexes that your application frequently accesses, fits comfortably within MongoDB's cache, which resides in physical RAM.
And you want the hot data in RAM.
Precisely. If the working set exceeds available RAM, MongoDB will constantly have to read data from disk, which is orders of magnitude slower. Key indicators that this might be happening are a high number of page faults, though some are normal, and significant I/O wait time reported by OS tools. These suggest your disks are struggling to keep up because data isn't being served from memory.
Okay. Now, in sharded clusters, you mentioned chunks moving between shards. There's something called the balancer that handles that.
Yes, the balancer is a background process that runs periodically in a sharded cluster. Its job is to automatically migrate chunks of data between shards to maintain a relatively even distribution of data across the cluster.
How does it decide when to move chunks?
This is a subtle but important point. The balancer primarily uses the number of chunks on each shard as its metric for balance, not the actual size of the data within those chunks.
Oh, interesting. So shards could have the same number of chunks, but very different amounts of data.
Exactly. If your chunk size is very significantly, maybe some chunks contain many small documents while others contain fewer but much larger documents, the balancer might think things are balanced based on chunk count, even if one shard holds significantly more actual data or experiences more traffic than another. This can sometimes lead to imbalances that the automatic balancer doesn't fix, occasionally requiring manual intervention, like manually splitting large chunks or moving specific chunks, to reestablish true balance based on data size or workload.
Good to know. Getting MongoDB truly production ready isn't just about starting the Mongo processes, right? There are specific system-level configurations and hardware choices that can make or break your deployment.
Absolutely. These are often overlooked but can have a huge impact. On the hardware side, using SSDs is highly recommended, especially for storing the journal files and the op log. The low latency of SSDs significantly benefits write performance and replication speed.
Makes sense. And the operating system.
64-bit Linux is generally the OS of choice for production MongoDB deployments. And specifically for the WiredTiger storage engine, the XFS file system is often recommended as it tends to perform well under MongoDB's workload. Now, here are a couple of non-negotiable system settings for anyone setting up a production Linux server for MongoDB. You must disable NuMA, non-uniform memory access, and transparent huge pages, THP.
Why is that? They sound like performance features.
They can be for some workloads, but for database workloads like MongoDB, which does its own sophisticated memory management, NuMA can lead to inconsistent performance depending on which CPU core and memory node handles a request. And THP can cause significant latency spikes and performance degradation due to the way Linux manages memory in large blocks, often conflicting with MongoDB's memory allocation patterns. Disabling both usually leads to much more stable and predictable performance. There are standard procedures documented by MongoDB for how to do this.
Okay, disable NuMA and THP. What other crucial settings should people be aware of?
Yes, definitely increase the system's file descriptor limits. The default on many Linux systems is 124, which is almost always too low for a busy MongoDB instance handling many connections and data files. You'll need to raise both the soft and hard limits significantly, often to 64,000 or higher.
Right, more connections need more file handles.
Exactly. It's also generally wise to allocate a modest amount of swap space, maybe a few gigabytes. While you ideally want MongoDB to never hit swap, as that indicates insufficient RAM. Having some swap space configured can prevent the Linux out-of-memory, OOM, killer from aggressively terminating the MonGOD process during brief, temporary memory spikes. It gives the OS a bit more breathing room.
A small safety valve.
Sort of, yeah. And finally, remember to disable or carefully manage any periodic background tasks on your production database servers, things like automatic OS updaters, antivirus scans, or unnecessary cron jobs. These can suddenly consume CPU or I/O resources at unpredictable times, impacting your database performance when you least expect it. Keep the database servers dedicated to their primary task.
Okay, let's talk protection. Security is obviously non-negotiable for any database holding valuable data. What does MongoDB offer in terms of built-in mechanisms to keep data safe from unauthorized access?
MongoDB takes security seriously and provides comprehensive authentication and authorization features. By default, authentication is off, which is why securing it early is vital.
Right, turn it on.
Absolutely. You enable authentication, typically using SCRAM, Salted Challenge Response Authentication Mechanism, which is the default and recommended method. MongoDB also supports using Pipe.509 certificates for secure authentication, both between the members of a replica set or sharded cluster, internal authentication, and for clients connecting to the database. Using TLSSL encryption for all connections is also crucial in production.
Okay, so authentication verifies who can connect. What about controlling what they can do once connected?
That's where authorization comes in, managed through a role-based access control RBAC system. MongoDB offers a rich set of built-in roles with predefined privileges. Examples include basic roles like read and read-write, administrative roles like DB admin for managing schema indexes, user admin for managing users and roles, cluster admin for managing the cluster topology, and powerful roles like root. There are also specific roles for tasks like backup and restore. You create users and assign them specific roles on specific databases, granting them only the privileges they actually need to perform their job. This principle of least privilege is fundamental to good security.
Granular control. Good. But beyond access control, how does MongoDB actually guarantee that your data, once written, won't just disappear if the server crashes or loses power? How does it ensure durability?
Durability is achieved through a combination of mechanisms. At the individual server level, the primary mechanism is journaling, which is enabled by default with the WireTiger storage engine. Before MongoDB acknowledges a write operation, it first writes the changes to an on-disk journal file in a sequential, durable manner. This means that even if the server crashes unexpectedly before the changes are written to the main data files, MongoDB can replay the journal during startup to recover those writes and ensure they aren't lost.
So the journal is like an immediate safe log of changes.
Exactly. But journaling only guarantees durability on a single server. To get durability at the cluster level, you combine journaling with the write concern settings we discussed earlier. Setting W majority ensures the write is replicated to a majority of nodes. Setting J true, often used in conjunction with W majority, ensures the write has also been written to the on-disk journal on that majority of nodes before success is returned to the application. This combination provides very strong guarantees against data loss, even in the face of primary failures.
Okay, so write concern controls durability for writes. What about ensuring consistency for reads? You mentioned read concern.
Right. Read concern allows you, the application developer, to specify the level of consistency and isolation you require for your read operations. The default, local, just reads the latest data from the node you're connected to, which might potentially include data that could later be rolled back if that node was a primary that failed before replicating. Using read concern, majority guarantees that you only read data that has been successfully written to a majority of the replica set members and is therefore durable and won't be rolled back. And read concern, linearizable, the strongest level, guarantees that your read reflects all successful writes that were acknowledged by a majority before the read operation started. This provides the highest level of consistency, but also typically has the highest latency impact.
So again, it comes back to that trade-off.
Yes, it's vital to reinforce that stronger durability and consistency guarantees, achieved through settings like W majority, J true, and higher read concern levels, often come with performance implications, usually in the form of increased latency for operations. The key is to understand your application's specific requirements for data safety and consistency, and choose the appropriate balance for your use case. Not every read needs to be linearizable, and not every write needs majority acknowledgement immediately.
Makes sense. Now, the ultimate safety net for any data system, no matter how durable or highly available, is having reliable backups and a solid disaster recovery plan. What are the best practices here for MongoDB?
Indeed. Backups are your last line of defense. You have several methods available. For instances using journaling, which should be all production instances, file system snapshots are often the recommended approach, especially if your operating system or storage system supports atomic snapshots, like Linux LVM or cloud provider snapshots. You take a snapshot of the underlying data volume. It's fast and consistent. If you can't use file system snapshots, or for older non-journaled setups, which shouldn't be used in production, you might need to use db.fsynclock to flush all writes to disk and block new writes temporarily while you copy the data files, or even shut down the MongoDB instance entirely to get a clean copy. But snapshots are generally preferred.
Okay, snapshots are good. What about logical backups, like exporting the data itself?
Yes, for logical backups, MongoDB provides the MongoDump utility. It reads data from the database and writes it out to BSON files. Crucially, for getting a consistent point-in-time snapshot of a live system, especially a replica set or sharded cluster, you should use MongoDump with the oplog option. This creates the data dump and captures the oplog entries generated during the dump process. When you restore using MongoStore, you can then use the oplog replay option to apply those captured oplog entries, effectively rolling the restored data forward to the consistent point in time when the dump finished.
So MongoDump oplog gives you that point-in-time consistency.
Exactly. It's vital for live backups.
What are some critical considerations when performing these backups in a live environment, especially with replica sets or sharded clusters?
Good question. For replica sets, best practice is generally to take your backup from a secondary member, preferably a hidden secondary if you have one. This minimizes the performance impact on your primary node, which is handling the application's live write load.
Right, offload the backup work.
Yep. And for sharded clusters, this is a really crucial point. You must temporarily disable the balancer process before starting any backup operation, whether snapshot or MongoDump, across the cluster, and keep it disabled until the backup is complete.
Why is that so important?
If the balancer is running, it might start migrating chunks between shards while you are backing up different shards at slightly different times. This could lead to inconsistent backups where a chunk might be missed entirely or backed up twice, potentially leading to data loss or corruption upon restore. So always turn off the balancer first.
Okay, that's a critical operational step.
Absolutely. And more generally, the importance of planning ahead for both your backup and your restore procedures cannot be overstated. Test your restores regularly. Understand how long they take and what the process involves before you're in an actual emergency. This planning allows you to minimize application downtime and impact during what could be very critical recovery situations. #tag outro.
So after covering all that ground, what does this all mean? As we've seen today, MongoDB offers, well, incredible versatility. It seems capable of powering everything from simple, small applications right up to highly scaled, globally distributed systems. It adapts to all sorts of data shapes and access patterns.
It really does. It empowers you, the developer or architect, with a lot of choices and control over how you model your data, the level of consistency you need, how you scale your system. But as we've hopefully made clear, understanding its underlying philosophies, the trade-offs involved in those choices, and how its core components like replication, sharding, and indexing interact, that understanding is absolutely key to leveraging its full potential effectively.
It's definitely not just a database in the traditional sense. It feels more like a powerful toolkit for managing data in the modern world. It gives you that flexibility to store complex, maybe messy hierarchical data naturally, and then provides the tools to scale that data horizontally as your needs grow.
Right. Which, raises an important question for you listening. Considering the flexibility and the power of MongoDB that we've explored today, thinking about its document model, its scaling capabilities, its aggregation framework, what kind of data challenge, maybe one you're facing right now or one you've thought about, would you tackle first to put this knowledge into action?
That's a great thought to leave with. Thanks for joining us on this deep dive into MongoDB. We really hope you feel much more informed and confident about what it is and what it can do. Keep exploring, keep learning, and we'll catch you on the next deep dive into the world of fascinating information.